How did we find a z-score yesterday? That was one of our big learning targets yesterday.
Score minus mean.
Good. The score minus the mean divided by the standard deviation. Okay, so anytime you're asked to find a z-score, okay, or a standardized score, this is what we're going to do. Okay, so what we need to do now, we're going to pick up our calculator and let it work for us. Okay, so we need to get a z-score for all 4 of his classes. All right, for all 4 of his classes, so that we can figure out where did Harry do the best and where did he do the worst. And remember, we got to do it in 2 steps, right? So that we don't mess up the math. Okay. So lucky for us, they put everything together right there, didn't they? So we'll take Harry's score, so 3.8, minus the mean, 3.75, divided by 0.15. Okay. So his first z-score was 0.333. Let's take 3 decimal places. Okay. Now, what does that mean, that z-score? Okay, so is he above the mean or below the mean? He's above, and he's only 0.333 standard deviations above the mean. Okay, so it's all about standard deviation. Let's do the same thing for the next one. So 3.6 minus 3.25, and then we divide it by 0.60, and we get 0.583. Okay, so there's that score. Do the same thing for transfiguration, 3.10 minus 3.20 divided by 0.38. Ooh, we got a negative this time. Why do we get a negative? Yeah, because Harry's score was under the mean, 263. Okay, and then 2.5 minus 2.9, and we'll divide it by 0.75. And we get in potions negative 0.533. Okay. All right. So now let's talk just a little bit about where we think Harry did the best. Okay. Which one's going to show us the best score? Which class?
The highest one.
Yeah, the largest one, which was what? Yeah, defense against the dark arts. And so that's good. Okay. So defense against the dark arts is going to be his best class, all right, because it is higher than the mean. His z-score is much higher than the mean. Okay. And then which one's going to be his worst class? Potions, right? Why potions?
That's the highest negative.
Yeah, that's the most negative one. Okay, it was the one farthest away. Okay, so that's going to be his worst class. All right, so just an interesting narrative, all right, for how we can use z-scores and what they're all about. Okay, so they help us to identify where we did really well and where we didn't do so great. Okay, we could do that in here as well with test grades and things like that to let you know how you performed with respect. I need all the phones away. Okay. And setting them up against your iPad like you can't see them doesn't work. Brooklyn. Okay. Put them away. Or we're going to have to start putting them up before lunch. All right. In the holder. Come on. Let's be grown-ups. All right. So now let's talk about what we're going to do today. Okay. So we're going to talk about a specific kind of distribution today. And how z-scores and all that kind of fit in. So we're going to use what's known as a density curve. But it's not always a curve, which is interesting. You're going to see, we see a rectangle in some of these. We're going to talk about relative locations of the mean and the median within those curves, and then talk about what's called a normal curve. Okay, you probably did a normal curve in Algebra 2. It's the one that looks like that mountain, a bell-shaped curve. So let's see what we get. Okay. So we're going to do a couple of things. All right, we're going to do a couple of things. And I think I got some number cubes, so let me get those out. We're going to roll a dice for a second. on each table. Let's see. If I don't, we'll just share them. So here's what we're gonna do. Okay, it wants you to roll 3 times. All right. So there's 2 for that table. The car is 6, by the way. I don't know what this came from, but the car is 6. Okay. So everybody needs to roll 3 times and record what you get. Okay. If you get the one with the car is 6. Okay. So you're gonna roll the dice. Everybody's gonna roll them 3 times.
Is there what, 3?
Yeah, we had one that was
6, 2, 4.
okay. So you just need to roll it 3 times. Okay. And put down what you get.
I gotta go to jail for getting another 3. I don't want to jail. Take it here.
Okay, so you can just roll them. All right, and then when you finish doing, you can put those in the basket. I'll put them up there.
She threw candy at me. How do you think it got to the ball over there?
Yeah, I
She
know
was
this
standing
was
there,
all the secret when I see
and she threw it at me and it hit the wall. She didn't pick it up. No. Okay, but look, I got attacked, brutalized.
Yep.
I got attacked.
You can drop it in the basket when you get them.
That's racism.
Okay, so let's talk for just a second about what's going to happen. All right, let's talk in theory. Did any of you get the same number more than once?
Yes.
Yeah. Okay. So if we think about the histogram for this bad boy, okay, when I rolled it, I got a 4, a 2, and a 1. Okay. And so mine were all different. And so if I think about my histogram, it would have looked like this. All right. So 1s, 2s, 3, 4, 5, and 6. Okay. So my frequency at 4, all right, I'd have 1 bar. At 2, I'd have 1 bar. And then 1, I'd have 1 bar. Okay, so mine would all look the same, all right? Some of you might have rolled 3 2 times, right? So yours might have looked something like that. Let me ask you a question. The more we roll it, what do you think is going to happen? We only rolled it 3 times, right? What if I rolled it 10? What's something that might happen if I rolled it? Yeah, I'm going to get some numbers are going to start to repeat, right? What if I rolled it 100 times? Even more, right? If I go 10,000 times. Yeah, we're going to get tired of doing it, right? We would hope we had a computer that would do that for us. But what do you think happens to the numbers as we get more and more rolls? What do you think happens to the number of times that we get each number? Yeah, it begins to equal out. Okay? It begins to equal out. And in fact, the actual histogram for this, if we rolled it, let's say 1,000,000 times. Okay? So if we did 1,000,000 rolls, like we did as many as we could get, we would find that it levels out and my distribution becomes, what do we call that when everything's the same? Becomes uniform. Okay? It becomes uniform. And that's what's really cool. I get 6, 1, 2, 3, 4, 5, 6. I did. All right. And that's one of the things that's really neat about rolling dice. okay? If all you're doing is rolling, over time, the more you roll, all right, it should equal itself out. And so we get this uniform distribution, okay? We would refer to all of the area underneath, okay, or inside that rectangle, all right, as a uniform density curve. Now, the word curve is funny to me right there because it's a straight line, okay? But that's what we call it. We call it a uniform density curve, all right? And then one of the cool things about it, right, is that the height on this side we would refer to as 1/6. And the reason we say 1/6 is how many sides are there on my dice? 6, okay? If I rolled it 1,000,000 times, my height should be 1/6 times 1,000,000, okay? And that's how we could get that frequency, which is kind of cool. So if I have 6 options, my height's 1/6. What do you think if I had a hexagonal dice? How many sides do you think is on a hexagon dice like that?
Is that 5 or 6?
I think it's 10. I think there's 10. No. Hex is 7, right? Decagon is 10.
Decagon is 10.
I got one. Hold on. Let's just.
I thought it was 6. Because a pentagon is 5.
Here's a pentagon. All right. Here's a pentagon. So it's got 1, 2, 3, 4, 5, 6, 7, 8. It has 11 sides. Isn't that weird? Okay. Anyway, it's 3-dimensional. All right. But here's the thing. If I had, let's say, a dice that had 11 sides on it, like that one did, okay? How many number options would I have on the bottom? 11. So then what would my height be? 1 out of 11, okay? If my dice had 40 sides on it, I have no idea what that would even look like, okay? How tall would it be? 1 out of 40, okay? It's 1 over however many sides it is, which is interesting, okay? Which is interesting. It can wait till lunch. Okay, all right, so that's important. When we're talking about a uniform density curve, if I have 6 options on the bottom, my height's 1/6. If I have 15, my height is 1/15. Okay, so it always matches. It's the fraction of the total that we have. Now, one of the things that's really cool about a density curve is that we can see the mean and the median. All right, so we know median is the same thing as the middle. Where would the middle of that curve be in that rectangle? It's not a trick question. They're literally in the middle, okay? So it would literally be in the middle. And that's what's nice, is in a uniform distribution, the mean is approximately equal to the median. It might be off by a smidge because nothing's ever perfect, all right? But the mean will equal the median, and that's important to know, okay? In a uniform curve, all right, so when it's a rectangle and everything's an equal amount, we will get the mean and the median in the middle. All right. Now we're going to skip task 2. We're going to come back and I'm going to talk to you about it in a second, but we're going to jump down here to task 3. Okay. We're going to get to task 3 and talk about it a little bit. Okay. So if you're aware, there's a timer, there's a stopwatch, so be it on your iPad. Okay. So let's find that widget, all right, on your iPad, because here's what we're going to do. We're going to turn our stopwatch on, and we're going to try to stop it at exactly 5 seconds, all right? And whatever number we get, we're going to write that down, okay? So let me show you. Let me jump over here and find mine. Oh, there it was. Clock, and we're going to do stopwatch, okay? Everybody's going to do it. You're going to do it 3 times. All right. If you don't have your iPad, ask if you can borrow your neighbor's. Okay. So when I hit start, I want it to get to 5 seconds. All right. Start. Stop. Oh, I got to 5.09. I'm going to write that down. All right. I'm going to reset it. Do it again. Can I get closer? Oh, no, I did bad that time. 4.68. I'm going to write that down. Then I'm going to do it one more time. Come on, come on. No whammies, no whammies. Oh, went too far. 5.33. Okay, I got bad reflexes. All right. So you're going to do that 3 times. Try to get as close as you can to 5 seconds. And then write your numbers down. Okay, Caitlin will get somebody with it. Good, write it down. Write it down. Okay, write your 3 attempts down. I don't know if they have one on the computer, if they're on the computer. Let me know if you hit 5 exactly. I'm going to let you buy my lottery ticket if you're 18. What? You missed it by just a little bit? Yeah.
4.98.
Oh, yeah, close. Woo! You're really trying to win. Look at you. That's impressive. Okay. So let's talk a little bit about our histogram. I really kind of made a boo-boo. But let's say that I started at, I'm going to actually, now leave that. I'll do 4.8, 4.9, 5, 5.1, 5.2, I did real bad, 5.3, and so on, okay? And so if I draw my histogram, it would look something like this. The first one was 5.09, so I had one that fell right here. 4.86, I had one that fell right here, and then 5.33, I had one that fell over here. Well, that's not a very good. Did y'all do better? Did you get closer? Did anybody end up with multiples within the same interval if we did them by tenths? Like you had, Eli, 4.99, 4.98, so you would have had 2 right here, okay? Lots of interesting things going on. What do you think's gonna happen as we get farther and farther away from 5? Will the bars get higher or lower? Yeah, I would assume too that they would get lower. All right. I think over time we would get really, really good right here. Okay, or maybe we spent most of our time here. But then as we go out, they should start to go down on each side, right? So if we just kept doing it over and over and over again, I think we would see our frequency increase there around 5, okay? What kind of shape is that distribution? It's symmetric, okay? It is a symmetric curve. And so when it's symmetric, we refer to it as a normal distribution. Okay, we call it normal. So if it's symmetric, we call it normal, right? And what's kind of cool about things being normal is that guess where the mean and the median still are? They're in the middle, okay? Again, they may not be exactly equal, but they're pretty close, okay? So that the mean is pretty much equal to the median, and that's nice. So if I have uniform, the mean and the median are right there in the middle. If I have symmetric or a normal curve, the mean and the median are right there in the middle, okay? So what were the other shapes of distributions that we had, by the way? We had skewed ones, right? Things that were skewed right or skewed left. And so if we had done number 2, the reason I didn't do it, because the last thing we need to be doing is making it hail up in here with throwing pennies. But, okay, if we start to throw pennies and we were doing that distance, we would get some skewed data, okay? So I want to show you what those look like, all right? So let's say we have one that looks like this, a distribution, all right? That looks like that. What would we call that one? Skewed left or skewed right? Skewed right, okay? We would call this one skewed right. And one of the crazy things about things being skewed right, all right, is that the median is going to always come first. And then the mean. Okay, so one of the things that we say is that the median is is less than the mean. I said that backwards. It's less than the mean. Okay, so if we read it from left to right and it's skewed right, the median would come first and then the mean. Okay, well, guess what happens when it's skewed left? Okay, so when we skew it left, my median is going to come second. And my mean would come first. And so in this one, the median's greater than the mean. Okay. Now, one of the things that we're going to be working on today, all right, is working with all of these different types of curves, okay? One of the things you're going to have to be able to tell me is where are the mean and the median, depending on what kind of distribution we have, okay? So the only time that they're not equal is when it's skewed, okay? And what I like to think of is when I'm looking at the skew, the median always falls at the tallest part of the skew, all right, or pretty darn close to that. So that helps me to be able to identify median's going to be at that tallest location. When we have something that's uniform, like we did up there at the top, okay, one of the things that we can do is we can calculate area, all right, that's shaded in. So if I know it goes out to 6, and the height is 1/6. How do we do area of a rectangle, by the way? Length times width. What happens if I take 1/6 times 6? 1/6 times 6. You get 1. Do you know how much 1 represents in terms of a percent underneath here? 100. Okay, it means 100% of my data is underneath that uniform line. Okay, and that's the reason why. So we're going to be able to find some percents, how much data, okay? If the median's in the middle, and the mean's in the middle, how much is less than the mean? Half, so 50%, right? So we're gonna use a little bit of geometry just in an area today, nothing crazy, length times width, all right? And then we're gonna talk about how do we set this up so that something is uniform, and that's kind of what we're gonna do when we get back, all right? And look through the examples, not terribly difficult, but what we're going to be messing with, okay? All right. Well, chill, we'll go to lunch in just a second.